It's science, but not as you know it. The Naked Scientists.
Hello, welcome to this week's Naked Scientists with me, Chris Smith, and also with Richard Van Norden. Hello, Richard.
Hello.
Now, coming up, we're going to be hearing how scientists have made a paper that's tougher than steel, and it's all thanks to some nifty nano-engineering. So that means we can do some vigorous sneezes in the hay fever season, and we won't end up blowing a hole in the hanky. There's also been a breakthrough in understanding how cancers spread around the body, and we'll be finding out how that works. And we'll also be talking to a scientist who's just broken the record for germinating the world's oldest seed. It was 2,000 years old. That's all on the way. Richard.
Thanks, Chris. Also this week, we'll be hearing about some hot research in the field of volcanology. So we'll be finding out how analysing the gases coming out of a volcano can give you clues about when it's going to erupt. And we'll also be hearing about a different volcanic beast entirely, the mud volcano. And there's one in Indonesia at the moment that's been going for 2 years, and it's spewing out millions of gallons of mud. And there's even one of these in Britain. We'll tell you where later in the show.
Plus, we've also got the answer to this week's calorie-conscious question of the week.
Recently, a friend of mine was telling me about a pizza that he burned to the point of becoming a charred husk 10 times smaller than the original. This pizza had now become a very low-calorie alternative to its former self. This led me to wonder whether all types of cooking result in lots of calories as well.
And the answer to that is coming up on the way with Diana O'Carroll. Plus, in a daring kitchen science this week, Dave and Ben have created their own kitchen-based volcano.
Well, I'm just going to gently feel through the flour and then just... Oh, crikey.
And if you want to have a go at that experiment, they'll tell you how to do it, but you're going to need a balloon, some scissors and some flour. Richard.
Thank you, Chris. So if you've got a question for us about volcanoes or geology in general, do get in touch. Email chris@thenakedscientist.com.
The Naked Scientists podcast, powered by UK Fast, the UK's best hosting provider, on the web at ukfast.net.
Well, let's take a look at some of the hottest stories that are emerging from around the world of science this week. Richard, what's all this about making indestructible hankies and very hard-wearing paper?
It's going to be a lot harder to punch your way out of a paper bag now, Chris, because some Swedish researchers have made this new super paper, and they say it's stronger than cast iron. And yet it's still made out of the cellulose fibres that make up normal paper. Now, the key to this is in the structure of the cellulose fibres in the paper. Normally, cellulose is a very, very common component of wood and of plant cell walls, and it gives them their strength. But unfortunately, the way we pulp paper to make our usual paper is that we use very strong mechanical processes which damage the fibres. So what Berglund's team did was use enzymes, bugs, to break down the fibres into nanometer-sized structures that's thousands of times thinner than a human hair. And these structures, which are really undamaged fibres suspended in water, that's what gives the paper its remarkable strength.
What sorts of things do people think we could do with it, apart from obviously hankies and loo paper that will avoid embarrassing environmental consequences?
Well, the key thing here, says Berglund, is they could be used as reinforcement. So apart from obviously reinforcing paper, they could produce something like extra strong sticky tape that's very hard to pull. Or they could help create really tough synthetic replacements for biological tissues.
And the fact that this is so hard wearing, this paper, doesn't mean that it won't break down in the environment. It won't have an environmental consequence.
Well, just like wood and cellulose, it will break down as well as those do. It is just paper, but just the internal structure is different.
Fantastic. When will we be looking forward to having some of this?
Well, Berglund doesn't say. This is still at the lab scale, so this is one of those discoveries that's going to take some time to come through.
So powerful paper on the way. Well, here's an interesting piece of research. It comes out of MIT from Robert Weinberg and his team. They've got a paper in the journal Cell this week where they have discovered or made an important step forward in understanding how cancers spread around the body. It's very often when you get a cancer that it's not the primary, the first tumour that you die from, but the spread around the body that in fact proves fatal. And what they've discovered is that if you implant into mice a human cancer, say a breast cancer, that grows very aggressively, and then elsewhere on the mouse they implanted a small trace of cancer, it was a type of tumour that grows only very slowly and indolently. It doesn't spread very much, so it's not a very good cancer, if you like. It hasn't learned to be aggressive yet. The pairing of those two together meant that the breast cancer could drive the growth at a very fast rate of this other tumour, and this told scientists it must be sending some kind of message through the animal's bloodstream, which is making the other cancer become very aggressive and speed up. Now, why this is important is that if cancers do spit off small cells which can go elsewhere in the body and take root somewhere, but they haven't learned how to be an aggressive cancer at that time. What might be part of the disease process is that the first tumour, when it learns to do this, then starts recruiting all these other cancers around the body and making them speed up.
So is that going to provide a way of stopping this type of cancer spread?
That's what they're saying, because they analysed the bloodstream of these mice and homed in on a chemical signal called osteopontin, which it comes out of these breast cancer cells, goes into the bloodstream, and this is the really amazing thing. It goes into the bone marrow. It gets stem cells from the bone marrow to come out of the bone marrow and join with the other cancer and feed it. And it's the presence of these bone marrow cells that makes the other cancer speed up its growth all of a sudden. And if they knocked out or stopped the animals making this osteopontin signal, then the other tumour didn't grow much faster. And they're saying that if we use this technique, it could be a way of actually interrupting the spread of cancer, perhaps while you give someone some treatment, so you can effectively slow down the disease and buy time while you find a way to get rid of it.
Well, that's astonishing. Now, some other amazing research come out this week in the journal Nature, suggesting that tree leaves, whether it's hot or cold outside, when they're at work photosynthesizing, turning carbon dioxide and light into the sugars they need, they stay exactly the same temperature and they have their own internal thermostat. Now, incredibly enough, the way this was done was to look at tree species from icy northern Canada all the way to hot Puerto Rico, looking at the ratio of isotopes in the wood, which should have been fixed just after the leaves were doing photosynthesis. Now, according to theory, these isotopes tell you what the temperature is outside because they vary according to temperature. But the researchers found the isotopes were telling you that these modern tree leaves should have been at a fairly constant 21 degrees Celsius.
So who's got it wrong? Is it the isotopes or is it the trees that are not changing?
Well, it turns out the weather outside had dipped to -10, so it looks like that the tree leaves do actually keep at a constant temperature. And Brent Helliker, who is one of the guys doing this research, suggests that the trees in cold climes actually group together to sort of trap in a layer of air and keep themselves at constant temperature. But as you just suggested there, Chris, it is not very clear whether the isotope ratios are a good way of measuring climate temperatures. People have used this concept to look at the temperatures for millions of years ago, and this is suggesting maybe that's not such a good way of finding out what temperature tree leaves are, if they do indeed have some kind of internal thermostat.
If they do have some kind of internal thermostat, what's the point of it?
Well, the point is that during photosynthesis, you don't want it to be too hot, or your cell membranes might get destroyed. You don't want it to be too cold, or your enzymes might not work properly. So really, leaves have invested a lot of energy in working out how to get their temperature the same all the way through their photosynthesis.
Well, let's stick with the subject of plants, because also in the news this week, scientists have confirmed that a pip that they've planted 2,000 years after the fruit that it came from was actually eaten is officially the world's oldest seed ever to germinate. And to tell us the story of this extraordinary bit of horticulture is Dr. Sarah Salon, and she's from the Louis Burrick Natural Medicine Research Centre in Hadassah Hospital in Israel, and she joins us now. Hello, Sarah.
Hello. Hi, Chris. How are you?
Very well, thank you. Thank you for joining us on The Naked Scientist. So, where did this 2,000-year-old seed come from?
Well, the seed is a date seed, and it was discovered at the archaeological site of Masada, which is Herod's palace, built above the Dead Sea, about 2,000 and something years ago by King Herod.
So what was the seed still doing there? Why hadn't it already germinated?
Well, the seed was, well, we think that, according to history, that the seed was part of the food supply of the Jewish zealots who had barricaded themselves into Masada in about 67 of the Common Era. And the Romans finally laid siege in 73, and for around 9 months, they subsisted on all kinds of food that they'd taken up there. And we know from the records that there were about 900 men, women, and children, and that on the very last day of the siege, they committed suicide rather than be taken alive. And when the Romans burst in, there was no one there to fight them, so they basically smashed the place to pieces. It was a magnificent palace, and it was just really demolished by the Roman legions. And these seeds were found 2,000 years later by Professor Yadin, who was a very famous Israeli archaeologist, when he started the excavation of Masada in the 1960s. And he discovered under a pile of rubble a whole cache of ancient seeds, of which quite a few of them were date seeds.
And why, since the 1960s, I mean, where have they been, these seeds, if he discovered them in the 1960s?
Well, they've been in the university. They were stored in the department of in Bar Ilan, which is a university in Israel, in the department of botanical archaeology. Actually, the Department of Life Sciences, but it's where they keep botanical artifacts from archaeological excavations. And they were there for 40 years until I had the idea, as part of a larger project that we have, on looking and researching and restoring Middle Eastern plants that were found in this region and which continue to be found in this region. And I had this idea to see if we could get some seeds from archaeological sites and to try and grow them, because that particular date no longer exists in Israel or anywhere else. It's extinct.
How do you know it's 2,000 years old?
Well, I don't, because I didn't do the carbon-14 dating, but we sent off 2 control seeds to the University of Zurich, their radiocarbon lab, which is one of the best in the world. And the 2 control seeds that were from the same site and were all stored at Bar Ilan came back as 2,000 years old, in fact, plus or minus 50 years around the siege period. And then when our little date seedling, which we nicknamed Methuselah, was about a year and a half old, as it was being taken from its small pot by Dr. Soloway, who's the lady who germinated it, into a larger pot, she found tiny fragments of the shell still attached to the rootlets. And then we sent those fragments to Zurich, and the result came back about 2,000 years. So we were very excited because that was direct evidence of its date.
So why did you decide to plant this in the first place? Because you must have thought, there's no hope in hell this thing's going to grow. It's 2,000 years old.
Well, I never do things that I don't think there's any hope. If I didn't think there was any hope, I wouldn't have done it. I was so optimistically thinking that there could be. And there had been other stories in the literature from China of a 1,300-year-old lotus seed, seeds from the Natural History Museum that germinated during the Second World War, when there was an incendiary bomb and a lot of water was used to put them out. And some seeds in the Natural History Museum germinated in this period. So I was kind of excited, and we had these, with some difficulty, we got them from Bar Ilan University. And it was part of our project on Middle Eastern plants, which is to research the plants of this region, which are highly medicinal, many of which are mentioned in the Bible and also in the Quran, and to conserve them and to redistribute them in Israel where they have been destroyed, and to study them for their activity based on their traditional use.
And when you did some genetic analysis on this plant, is it similar to date plants that are still around today, or is it different?
Well, Chris, if anyone that's listening to this who's a geneticist, they'll know that taking a seed which is produced from sexual reproduction, which the dates are, because dates are male or female, so taking one seed will not really give us any kind of confirmatory evidence of its genetic characteristics, because you need a population to give you an understanding of the genetic characteristics. But just looking at one seed, which is all we've got at the moment, it does seem kind of different from the standard cultivated date species that are around these days, which originate in Morocco, Egypt, Iraq, and which are growing now in Israel.
So will it be possible to breed from this plant that you've managed to regrow, or is there a chance that it might not be female and therefore it's going to be a lonely male and will never reproduce?
I think that's a very sad statement, that it might be a lonely male. It could be. We just don't know, and we won't know until it's about 6 or 7 years old before we see whether it has female reproductive organs and is therefore female, or whether it's a male. Now, if it is a female, then we have a chance of perhaps of producing dates using a male donor, if you like, or maybe we'll be able to germinate another seed.
Let's hope so. Thank you very much, Sarah.
Oh, it's a pleasure. Thanks very much, Chris.
Sarah Sallin, who is from the Louis Burrick Natural Medicine Research Centre at Hadassah Hospital in Jerusalem, talking to us there. And she has broken the Guinness Book of World Records for growing the world's oldest seed. So thank you very much to Sarah.
Stripping down science.
OK, let's do it.
The Naked Scientists.
Now, Richard, I've got a question here from Joyce, who says, what happens in scientific terms in the reaction between acid rain and limestone?
Yeah, well, what happens is that the carbon dioxide in your acid rain, together with your water, H2O, reacts with your limestone to give you, at first, carbonic acid, and that's chemically H2CO3. But then that further breaks up into H+, your hydrogen ions, and that's your acid. And then your bicarbonate, HCO3-, and that's soluble. And that is what gives you the hard water, that kind of gritty taste to water. And that breaking down is why acid rain destroys limestone, but that's what's going on chemically.
Thank you, Richard. Got an email here from Mexico. It's Felix Canes. He says, love the show. I'm listening in Mexico. I listen to it every week on the podcast. You guys do a great job, so thanks very much.
And another one from Ryan. Being a newly baptised neurologist in New York, I have missed many of my favourite shows on TV, he says. Yours is the only programme I follow every week. I love it. Thank you very much, Ryan.
Got a funny one here from Nick Bird. Hello, Nick. He's in Oklahoma. He says, I really enjoy listening to your podcast while I'm at my job of raising parakeets. My family sometimes think I'm crazy when I come home with one of your experiments to try. Incidentally, Dave and Ben are coming up on the way with their homemade volcano for you to try this week. I think that's quite funny because Nick, his surname's Bird, and he keeps parakeets. It's quite funny. This one's from Adrian, and he's in Romania. He says, why do glasses, cups and plates have a ridge around the base? Why not have a flat bottom? What do you think?
Well, that's a good question. I'm just trying to think about that one. A ridge around the base, presumably just to keep them stable, I would imagine. Unless they were, I guess you'd put them on the top and they'd be stable. I can't think of any other reason.
I think we had a little bit of a mini debate about this, and I think the reason is that if you have a thin ridge around the bottom for the plate to stand on, the pressure is highest there because it's not exerting the force downwards of the plate across the whole of the plate's surface, and that high pressure means the plate makes a much firmer contact with the tabletop, therefore less likely to aquaplane if there's damp underneath, so much less likely to sort of skid off and go wrong, slide onto the floor.
Well, there's certainly all sorts of possibilities for pulling off a tablecloth without getting rid of the plates that way.
Anyway, thank you very much, Adrian. Now, still to come, we'll be finding out how scientists can look at the gases that are leaking out of a volcano to find out when the next eruption's going to happen and whether it's likely to go with a bang or a bit more of a whimper.
But before that, Ben and Dave have been busy building their own kind of volcano, kitchen science style.
Hello and welcome to Kitchen Science. Now, this week's show is all about volcanoes, so I'm expecting there's going to be some big explosions in this one. I've come to Dave Ansell's garage where all the really dangerous experiments take place. So what's going on, Dave? Are we going to melt down some rock to see how molten lava flows? Are we going to set off an eruption in your garage?
I'm afraid no melting rock today, Ben, because that would be a bit dodgy. But we are doing a really neat experiment to show how some volcanoes form.
Oh, well, now that we've worked out that it's nothing dangerous, is this going to be something that people can do at home?
Yes, definitely. All you need is sort of about a bag of flour or an equivalent amount of sand or sawdust or something kind of granular like that, a small balloon, a pair of scissors, and possibly a box to keep everything controlled.
Oh, great. So this is an experiment using flour, so this really is a good one for doing in your kitchen.
Depends on your attitude to having flour spread or evenly over your kitchen, but you could certainly do it in your kitchen, yes.
So we're expecting a flour eruption?
Something along those lines, yes.
OK, how do we get this set up?
Well, the first thing you want to do is blow up the balloon. You want a small balloon and blow it up sort of slightly larger than a fist.
OK. OK, so yes, it's just a bit bigger than a cricket ball, so there's not too much air.
That's all right, so I'll just tie that off.
OK, so we have our balloon. What's the next thing to do?
Okay, so you want to put the balloon in the bottom of your box and then cover it in flour.
Do we need a thin, even layer of flour?
No, you want to form a nice cone like a mountain or a volcano.
So we need to make our own volcano, really, from the flour. But why is it that volcanoes are that cone shape anyway?
Well, many volcanoes have got lots of magma and ash being thrown up from deep underneath the earth through a tube. And that keeps coming out in one place and builds up and builds up. So the most stuff gets deposited near the tube and gets less further away, forming a sort of cone shape.
So you wind up with lots and lots of layers, and it winds up higher right by the entrance to the tube and lower the further away you get.
Yeah, that's right.
OK, so let's get our balloon buried now. We're going to bury it in a cone shape of flour. Does it matter which way up the balloon is?
Ideally, you want the place where you blew it up from at the top.
So you want the knot towards the top of your pile of flour?
Yeah.
And do we need to completely cover it?
Yes. Completely hide that balloon.
OK, so we have our flour volcano now. It's the right shape. The balloon is completely buried. And so far, we don't seem to have got too much flour all over the place, so what's the next thing we need to do?
We want to get your scissors and then very gently find that knot on your balloon and cut it off. You probably want to do this at arm's length, especially if you're using something like sand or sawdust or anything quite hard. Do it at arm's length, chop the top off, and see what happens.
This sounds like it's going to be very, very messy. A balloon exploding under a pile of flour. Surely all we're doing is making a mess.
Well, you can find out at home by trying it.
Well, we are going to save our flour volcano eruption until the second part of this week's Kitchen Science, which gives you plenty of time to give it a go yourselves and let us know what happens, or just let us know what you think will happen. We'll be back very soon.
Sometimes I think they're just looking for an excuse to make a mess, you know. If you want to try it at home, so you just have to get a small balloon, which you blow up to just more than fist size, then bury that in some flour with the knot uppermost, and then you slide some scissors in through the flour and snip the knot off the bottom. Have a go. Let us know what happens and what the result looks like. And I tell you, there is a serious observation to be made here, so we want to know what that observation is. If you're all out of flour, though, don't worry, because we'll be going back to Ben and Dave later in the show to find out what happens to them.
And if you have any questions, meanwhile, about volcanoes or geology in general, or you just want to say hi, because we love hearing from you, do get in touch. Email chris@thenakedscientist.com.
And one other exciting thing we do here on The Naked Scientist is that we beam this programme live into Second Life, and that's at 6 o'clock UK time, which confusingly enough is 10 o'clock in the morning in Second Life time. That's because Second Life actually is based in California, so that's why it's 10 o'clock in the morning. If you'd like to come and meet some of the other people who are in Second Life, hello to all of you. We're watching you, by the way, in Second Life. You go to Second Life, you visit the Scilands, SCILANDS, and just look for the Naked Scientist Mansion. You can drop by and you can relax on one of our sun loungers and listen to the programme and talk to all of our other listeners who are there.
The Naked Scientists. For more information, get online at nakedscientists.com.
Now, in a moment, we're going to be finding out how volcanoes can trigger earthquakes and how the patterns of vibrations that they produce could be used as an early warning sign that an eruption is about to happen.
But first, there's another way to find out what a volcano is up to, and that is sampling the gases it's producing. And erupting into the studio now from the University of Cambridge is volcanologist Marie Edmonds. Hello, Marie.
Hello, Richard.
First off, most people know what volcanoes are, but what's actually going on inside one?
Well, what we see at the surface with volcanoes is really only part of the story. So part of my work is looking at magma degassing and how looking at the gases that are emitted by volcanoes at the surface can tell you about what's going on deep in the crust.
What sorts of gases are coming out of volcanoes?
Well, volcanoes emit lots and lots of water, and then lots of carbon dioxide, sulfur dioxide, halogen gases, and various minor trace components. But water, CO2 and SO2 are the main gases.
And how can we actually analyse these gases and what do they tell us?
Well, I go with a spectrometer to the volcanoes, which is a really good way of doing it safely because I can go a kilometre or so away from the volcano. I don't have to go right up to vents and fill little glass bottles of gases. So I can use spectrometers to remotely look at the composition of gases and work out from that what's going on beneath the surface. So gases are, if you like, messengers from the interior of the crust.
What's a spectrometer? How does it work?
Gases absorb radiation in characteristic wavelengths, so each gas is associated with its own unique signature. So if we collect infrared radiation, say from the sun or from a lava flow or a lava dome, and the infrared radiation has passed through volcanic gases, so what we're looking at is a spectrum that contains all of the unique absorptions due to all the different gases, and we can quantify their concentrations.
So this is quite a neat way of being able to monitor the volcano without actually having to put yourself in quite a lot of danger by getting really, really close, because you can see what the gas composition is remotely.
Well, that's absolutely right. And in fact, volcano monitoring has come along a long way since the development of techniques like this. So in the last decade or so, really, these techniques have become a lot more sophisticated.
And what does this analysis of the gases tell you about the behaviour of different volcanoes?
Well, the idea is that each volatile species, so water, CO2 and so on, they exsolve at different pressures. So as magma is coming up from the base of the crust, first of all, carbon dioxide will exsolve. And then when it gets to very shallow levels, gases like water and SO2 exsolve and form bubbles in the magma. So if we measure gases which have very high CO2 content, for example, We know that the gas is separated from magma at depths of a few tens of kilometres. If the gases are rich in water, then degassing is occurring at shallow depths. So we can infer something about the style of the eruption, and we can, to an extent, forecast volcanic activity this way.
Because most people think of a volcano as this thing that just either blows up fairly catastrophically, like Mount St Helens, which is in every geography textbook as the massive explosive volcano, but others are sort of more oozy and they just splurge out lava without really doing much. Does one turn into the other, or is there a risk that one might be one of those kinds and then suddenly explode? I mean, what do we know about volcanoes behaving that way?
Well, there are a whole different range of volcanoes and different styles of activity, and I've actually measured the composition of giant bubbles that have come up, very low viscosity magma columns at Kilauea volcano in Hawaii, and then you can go to a completely different type of volcano, such as Soufriere Hills volcano in Montserrat, which is an explosive type of volcano, and crucially, it has very high viscosity magma. So this type is the most unpredictable, and in some ways the most interesting, because it can transform from fairly effusive dome-building activity to very explosive ash-producing eruption columns over the space of a few minutes. So that's what makes this kind of eruption particularly fascinating.
Because you're going back to Montserrat, aren't you?
Yeah, I've already done a trip there this year to measure CO2 fluxes through the flanks of the volcano there, because we still know very little about what goes on at depth and what's actually driving the eruption. So yeah, I'm due to go back in a few weeks' time to continue those measurements. We're going to install a gas sensor close into the volcano to try and measure the proportion of CO2 and SO2 in the hope that this will give us some idea of whether the eruption is waning or whether it's accelerating, what we can expect in the next few months in terms of activity.
I've got an email here from Darwin Teague, Marie, who says, how much pollution does a volcano produce? I've heard that volcanoes spew out as much pollution as all of the cars that have ever been built on Earth combined, but how much pollution does a volcano really produce when it erupts?
Well, this is a very good question, and it actually gives me an opportunity to dispel some of the myths about volcanoes and global warming and pollution. Volcanoes emit CO2 and SO2. Carbon dioxide and sulfur dioxide are the main gases that might be construed to cause global warming or pollution. Volcanoes emit around 100 million tonnes of CO2 a year. Compare that to man-made emissions of CO2, which comes to about 10 billion tonnes of CO2 per year. So volcanoes emit around 1/100th of the amount of CO2 that we do, and are therefore insignificant in terms of global warming. Sulfur dioxide, on the other hand, volcanoes emit around 1/10th of the anthropogenic emissions of SO2, and that, of course, forms regional smog.
Isn't there another benefit to sulfur dioxide, is in that it reflects heat back into space, so in fact it cools down the Earth, so volcanoes are quite good in that respect because they keep us cooler than we otherwise would be?
Yeah, there has been some research over the past few years that suggests that very large eruptions, such as Pinatubo in 1991, that eruption emitted around 20 megatons of SO2 into the stratosphere. And eruptions such as those, which happen once every decade, in fact have slowed down global warming a little bit. So without those eruptions, we'd actually see the effects of global warming much more now than we do.
There's a question coming from Edsel Heinkel, who's listening in Second Life, and he says, is there any way to stop or alter an eruption once it's actually got going?
Well, the quick answer to that is no. I think it will be foolhardy at best to try and interfere with the processes going on in a volcano. There have been instances of people trying to divert lava flows, for example, by spraying water on them and blowing them up with explosives.
And building canal systems for them to run into preferentially.
That's right. But actually, trying to alter eruptive processes at the vent wouldn't be advised, I think.
Quite adventurous. Thank you, Marie. That's Marie Edmonds. She's from the University of Cambridge. She's also a fellow of Queen's College, the best college in Cambridge, of course. So if you have any questions about volcanoes, you can send those in. It's chris@thenakedscientist.com.
The Naked Scientist Podcast, brought to you by thenakedscientist.com.
Now, still to come, we'll also be finding out why not all volcanoes involve streams of red-hot lava, because some instead produce millions of gallons of mud. Plus, we'll also be talking about hot stuff in another way, which is that in this week's Question of the Week, Diana O'Carroll will be finding out whether burning your food can actually help you to shed some excess calories.
But first, we've already heard how analysing volcanic gases can help us to predict future eruptions. But what about earthquakes, seismic activity? Here's Mira Senthilingam.
Just before a volcano erupts, there are often earthquakes of varying intensities. Scientists had already realised that the movement of molten rock, or magma, can often cause these quakes. But what they hadn't realised was that even at very high temperatures, when you'd expect magma to be soft, it can still fracture like brittle rock. And it's the vibrations triggered by these sudden fractures that go on to become the earthquakes that scientists pick up. This was discovered recently by UCL researcher Professor Peter Sammons using his very own laboratory-based volcano.
Well, what we did was in the laboratory actually try and simulate the conditions of a volcano. Pressures up to a few megapascals, temperatures up to 1,000 degrees centigrade and even higher.
In front of us we've got a rather large metal structure with dials on one side, and in the centre there's large metal cylinders with larger cylinders kind of sprouting out from the top, and it's all connected to a computer as well. So how did you actually go about recreating volcanic conditions with this metal instrument?
Well, the lower part is what we call a pressure vessel, so that contains a gas at high pressure. We put the rock specimen in there, our typical sort of test specimens, cylindrical cores about 25 millimetres in diameter, about sort of 75 millimetres in length. We then heat the specimen up with an internal furnace to sort of 900,000 degrees centigrade. Then we have the piston, which is driven down onto the rock sample until the rock starts to fracture. And then using an acoustic transducer, it's a bit like a microphone really, listening to the acoustic activity or microseismicity to see how the rock at this very high temperature was fracturing and then sort of the nature of that fracturing.
We have two of the samples that you actually used during the experiments. What are these?
Well, we used two quite contrasting samples. We've got a sample of lava from Mount Shasta in North America, which is a crystalline lava. It's called an andesite. And also we used an obsidian, which is a glassy lava from Krafla in Iceland. So in a sense, these represent the two end members of rock types you might wish to look at, a glass on one hand and a crystalline rock on the other.
So having actually put the samples inside and recording the seismic activity, what did you find?
First of all, of course, we actually found that we could actually get these rock samples fracturing up to about 1,000 degrees centigrade. It's actually showing that actually you do get fracture at very high temperatures in rock. So we could deduce that certain types of earthquakes are maybe caused by this high temperature rock fracture. The second thing I think we showed was that we had the patterns of seismicity coming up towards fracture had particular characteristics about them, sort of indicative that a through-going fracture was going to occur.
So what volcanologists are now hoping is that if we can understand these patterns of activity a bit better, we'll be able to predict when a volcano might be about to erupt.
Mira Senthilingam talking to Peter Sammons there from University College London about their earth-shattering discovery that even hot magma, the molten rock beneath a volcano, can shatter and trigger earthquakes.
Boom, love the pun. This is The Naked Scientists with Chris Smith and with Richard Van Norden.
We're talking about the science of volcanoes this week, so don't forget to have a go with Ben and Dave's Kitchen Science Experiment. We'll be catching up with them again later, but just to remind you, inflate a balloon, bury it in a pile of flour, and then use some scissors to snip off the neck of the balloon. Please let us know what happens. Email Chris at thenakedscientists.com.
And incidentally, we've heard from Crystal Falcon, who tried the Kitchen Science volcano effect and says it obviously blew some flour up, but what I wasn't expecting is how it all collapsed. So there's the key clue to the observation you're going for. So just to remind you, put this balloon that you've blowed up, neck upwards, in some buried flour, trim off the neck, and tell us what happens, if assuming you can see through the pile of dust that you get afterwards. Now, volcanoes are not necessarily all about lava and hot rocks. They can actually be powered by mud as well. And in 2006, a company that was drilling for gas in Indonesia accidentally set one off. And Professor Richard Davies is a researcher. He's based at Durham University, and he's been studying a volcano which has been christened Lucy. So, hello, Richard. Thank you for joining us. How much mud are we talking about coming out of one of these things?
Well, it's been erupting about 150,000 cubic metres per day for the last 2 years, basically. It now covers 7 square kilometres. It's about 20 metres thick in its central parts and then sort of feathers out, a bit like a pancake, basically.
So when we say a mud volcano, is it genuinely mud that's coming out?
Yeah, it's a mixture of mud, a lot of water, saline water, and gases, methane, hydrogen sulfide, carbon dioxide. So it's a mix. It's about 79% water, and the actual mud is about 20%. So it's a very dilute mud volcano.
And what's the impact on the local environment of this?
Well, unfortunately, this is the only mud volcano that's really erupted into a highly populated area. So 30,000 people have lost their homes. There's been 13 fatalities. There are factories that have had to close, schools, etc. And because this thing is carrying on and developing, all sorts of other things are starting to happen. The area is subsiding. The central parts of the mud volcano are subsiding at 4 centimetres per day. And it doesn't take long to work out that's about 14 metres per year. So as long as the mud volcano continues, the effects are going to increase. And one can only speculate that perhaps in 10 or so years' time, if it's still erupting, that rivers may have been redirected. All sorts of environmental impacts will have occurred.
And geologically speaking, what is actually going on underneath this mud volcano?
Well, down about 3,000 metres depth, there is a limestone called the Kajung limestone. And this is a fantastic aquifer. It contains a lot of water. It has a lot of permeability, which means the water can flow very easily. And that is leaking up into a mudstone, which is a couple of thousand feet higher up. And then it's pulling with it the mudstone and bringing it to the surface. It's driven by pressure, but also there's gas in the mud-water mix, and that gas is also probably providing some of the lift mechanism in similar ways to the earlier speaker who talked about igneous volcanoes.
And what do we think triggered this to happen?
Well, it was almost certainly triggered by the drilling of an exploration well. We've now got detailed data from the well. The well was being drilled 150 metres away from where the eruption started. And we know that on the 27th of May, overnight, going through to the early morning on the 28th of May in 2006, they had some major operational problems. I'll summarise what actually happened. Basically, they had what is called a kick, which means there was an influx of gas and water into the wellbore. And the only thing that they could do when this kick occurred to stop the water and gas coming to the surface was to shut in valves at the surface. When they shut those valves in, they recorded pressures that went beyond the critical pressure at which the underground rock started to fracture. So the fractures basically developed and propagated to the surface. So on the following morning, on the 29th of May 2006, mud, water and gas started to erupt.
But the company, they've gone on record as saying that, in fact, it was a local earthquake that did this.
Well, it's not so local. It was 280 kilometres away, 6.3 in terms of magnitude. And it's been shown by Michael Manga, who's a professor in Berkeley, that this earthquake would have been too small and too far away. So in the paper we've just published, we show in the first part of the paper that the earthquake was really just too small and too far away. And the second part of the paper lays bare all the data and all the facts about what actually happened with the drilling of this exploration well.
So this thing has been going for 2 years. When's it going to stop?
Very good question. It's gone on for 2 years pretty much unabated, which means they have tapped into a very, very good aquifer. Now, we can try and estimate how long it will continue for by looking at the size of the aquifer, the original pressure in the aquifer, and how long it would take for that pressure to drop to normal levels. But the fact it's been going on for 2 years without showing signs of stopping means I think it will go on for many years to come. Even when the pressure has depleted, there will be gas in the system, and the gas provides a lift mechanism as well. Just like taking the lid off a Coca-Cola bottle, essentially, the gas will pull the mud up. It will give it some buoyancy.
Do you think that this is an isolated case, Richard? Because we've had an email from Michael who says, will removing oil, for example, destabilise the Earth? And obviously the answer we trot out is, oh no, the oil volume relative to the crust of the Earth is very, very minor. But situations like this highlight the fact that, in fact, there can be consequences.
This does happen. This is something that happens probably a few times a year around the world. What's happened here has been unfortunate in that the area was ready for a mud volcano to form. In other words, the geological conditions were suitable. Unfortunately, this company drilled a well which had operational problems which provided the pipework, the plumbing, so that the mud volcano would form. But, this is something that happens a handful of times each year. This is the worst case in that, unfortunately, in this case, It happened in a populated area, and it brought a lot of mud with it.
And I think people will probably be quite surprised to learn we do actually have one of these in Britain, although thankfully not on the scale of the Indonesian example.
Yeah, I'm delighted to say it's nowhere near on the scale of the Indonesian example, and it is a natural occurrence. So these are very small mud volcanoes outside Swindon. But what I like about them is that they provide an analogue for what's happening in Java right now, in that it's actually, again, a limestone, the Corallian, which is a Jurassic age limestone, about 160 million years old, that's supplying the fluid. And the fluid is then passing through a clay called the Apt Hill clay, and the clay is being brought to the surface. And it actually has within it a number of beautifully preserved ammonites.
So that saves fossil hunters a bit of effort. Richard, thank you very much.
Thank you.
That's Richard Davies from Durham University describing the phenomenon that is the mud volcano. It's The Naked Scientists with Chris and Richard, and we're talking volcanoes this week. Marie, we've had lots and lots of questions come in. Law Gynoid, who's listening in Second Life, says, can we harness volcanoes to modify the environment?
Well, I think what we can do is harness geothermal energy. So usually we wait for volcanoes to be in periods of unrest and not active eruption in order to do this. But this is certainly done in Iceland and also New Zealand.
And we also had this question, which I thought was terrific. Pookie Amsterdam suggests, why don't you just stick a cork in a volcano? Will that presumably make it erupt elsewhere?
Well, that's a very nice idea, but in practice I think that wouldn't work. Enormous pressures build up in conduits and magma chambers beneath volcanoes, so I think you'd need a very large cork.
And we also have a question from Cliff Taylor. He says, I found a crystal on a beach that looks like glass where it's broken, but it looks like a mineral on the bits that aren't broken. Now, we can cut glass with it, but it doesn't affect the stone, the crystal. And he wants to know if can only a diamond cut glass?
What do you think it is, Marie? Do you think that's volcanic glass?
Yeah, it certainly could be volcanic glass. There's a glass called obsidian, which is a silicic magma, and the way to recognise it is if you've got a fractured surface and it's curved. So glass generally forms these curvy planar surfaces when you break it.
Got another one here from John Berger. He's in Vancouver Island. He says, if the Earth's core is made of heavy and dense metals, mostly iron, are the most dense metals at the centre of the core? So in other words, if we were to drill down 6,000 kilometres, would we find enormous quantities of things like gold and uranium and osmium?
Yes, certainly called what we call refractory elements, such as osmium, iron, nickel. So throughout Earth's history, all of these heavy elements have been migrating towards the core, and all the light elements have been migrating up to form the crust. So, yes.
Because aren't there some companies that are being formed and they want to exploit the minerals that are being brought to the surface in hydrothermal vent systems? Because aren't they enriched for minerals and things that are actually quite hard to get hold of? But because the Earth's geologically doing the work for us, then that's a useful way to do it. They call it sort of surgical mining, where you just scrape the seafloor and up come these minerals.
Yeah, certainly hydrothermal systems around volcanoes. Fluids actually bring a lot of these metals, like gold, like silver, up into the volcanic edifice, and they get precipitated in hydrothermal systems. So a very easy way of mining these is to dig into a volcanic edifice where they're concentrated.
Got an email here from Cheryl Holy. She says, I love your show and I listen to it while I'm mucking out stalls. Thank you, Cheryl. That's wonderful. I'm pleased that we provide some distraction from what must be a bit of a tedious job. I've been pondering a question about climate change and global warming. If the polar ice caps melt and the weight of all that water gets redistributed around the planet, and given that the planet is just a ball of molten stuff underneath a relatively thin crust, will the shape of the Earth change? Will it bulge more in the middle? Will it spin differently? Or will the axis change? What do you think, Marie?
The answer to that is probably no. In fact, that's a common misconception that the Earth is entirely molten. In fact, the Earth is mostly solid. It's only the outer core of the Earth which is liquid. So the entirety of the mantle is a solid. And it actually behaves very much like a solid, very high viscosity.
Although having said that, isn't England rising in Scotland? For instance, Scotland's going up and England is dropping a bit because the ice sheet retreat means we took the weight off and things are changing.
Yeah, there are. That's absolutely right. After the ice age, when ice sheets melt, there is what we call isostatic rebound following the removal of ice sheets. So that's on a regional, local scale.
Thank you very much. That's Marie Edmonds from Cambridge University. This is The Naked Scientists with Chris and Richard. And if you have a question for us, email chris@thenakedscientists.net. UKFast.com. Richard.
Now, Diana O'Carroll is here, and she's going to tell us whether burning your lunch can turn it into its low-calorie counterpart. So, Diana, what's all this about taking char grilling to the max?
Hello. Well, we're going to do a bit of a volcanic experiment inside an oven this week. So we've got some molten lava pizza.
Hi, I'm Alan Wensky from Berkeley, California. And my question is one regarding pizza. Recently, a friend of mine was telling me about a pizza that he burned to the point of becoming a charred husk 10 times smaller than the original. At that point, I realized that this pizza had now become a very low-calorie alternative to its former self. This led me to wonder whether all types of cooking result in loss of calories as well. For instance, does a perfectly cooked egg or piece of toast also have less calories than the original?
So, can reducing the size of your pizza through incineration actually cut down on its energy?
Hi, I'm John Fry. I'm a food scientist and a chemist, and my specialty is low-calorie foods and drinks. Well, burning the pizza will certainly reduce its energy content because some of the energy that you might otherwise have digested and turned into you goes up in flames and smoke. So the black carbon that's left after you've burnt the pizza has got a lot less energy in it than the original. Other cooking processes also cause loss of fat. Roasting a joint of meat is a good example. But it's also common to rescue the fat and meat juices that drip from the joint for use in gravy, or that great staple of my youth, bread and dripping. But cooking can also directly increase the energy content of food by making it more digestible. Starch, in particular, is made more easy to digest by cooking it. Starch crops up as small, tight granules in many cereals, vegetables and fruits. Humans are thought to find it easier to digest starch once these granules have been burst open and the starch released in a gelatinized form by cooking. In short, cooking can increase or reduce the energy content of a food depending what you do. But if you want to eat fewer calories, then consuming less food is preferable to incinerating your pizza. Burnt food may have fewer calories, but it also contains a lot of very toxic materials created by excessive heat, and it doesn't taste that great.
Sadly, the O'Carroll burnt pizza diet will not be in press anytime soon, as extreme baking will only remove water and a small amount of fat. It may also be the case that the starch in the pizza dough will become more calorific as cooking makes it easier for your body to absorb the carbohydrates. Well, that's before it becomes burned to a crisp. On our forum, both Neil P. and Jay Petruccelli describe the carcinogenic effects of food burning. So next week, let's look at a little more in the way of heartburn.
Hi, I'm Becky from Bishop Stortford, and my question is, as lightning can strike in the same place twice, if you get struck by lightning and it stops your heart, and then they get struck by it again, would it restart your heart?
And from lightning defibrillators to seeing the pretty colours, I'll be finding out about copper.
Hello, my name is Vivian. I'm calling from Adelaide in South Australia. And my question is, why is copper the metal, copper in colour, yet when in solution with copper sulphate it's blue and copper carbonate it's coloured, and when you do a flame test it's actually green?
So, can 2 strikes of lightning be a lucky event? And why is copper such a colourful metal in its various forms? Send your answers to me at questionoftheweek@thenakedscientist.com or write it all in our fabulous discussion forum at thenakedscientist.com/forum.
Thank you, Diana. You have to be pretty unlucky to get hit by lightning twice. So someone's trying to tell you something if that happens.
I think so. Don't play golf.
Funnily enough, the guy who was the chief executive of PowerGen when it existed, the motto of PowerGen is generating power whatever the weather. He was on the golf course and he got hit by lightning.
Ouch.
Don't know if he had an umbrella or not, though.
Laying the facts bare. The Naked Scientists.
And it is The Naked Scientists with Chris Smith and with Richard Van Norden.
It's now time to go back to Ben and Dave erupting their homemade volcano.
Welcome back to this week's Volcanic Kitchen Science. Earlier on, we asked you to get a balloon, blow it up to a size a little bit larger than your fist, and then bury it in a mountain of flour. You need to make it the right cone shape. So think of all the volcanoes you've seen pictures of or seen on TV and make it the right shape for that. And what we asked you to do at home was use a pair of scissors and very carefully cut the knot from the top of the balloon and see what happens. Now, our volcano is still set up here and we haven't yet caused the eruption. So, Dave, are we ready to go?
Don't see why not. Let's try it.
Once again, if you're doing this with sand or sawdust or anything a bit harder than flour, it will work, but you do need to be careful in case it throws anything into your eyes. We're doing it with flour, so we don't need to be quite as careful. So, Dave, what have we got to do?
Well, I'm just going to gently feel through the flour to find the knot on the balloon, and then just chop.
Oh, crikey, Dave. Well, that was certainly a flour eruption. The balloon burst. It didn't go pop, but it did throw flour all over your garage. You're going to have quite a job to clean up all this flour. But now that it's clearing, I can see what we're left with is a crater in the middle of our volcano. I would have expected that the balloon would blow up, it would just blow up the whole cone shape. But what we're left with is very much like the craters that you see in volcanoes in photographs. It's quite impressive. It has quite a sharp ridge and then a circular crater in the middle. Dave, how did this happen?
Technically, this is known as a caldera. It's the things which look like giant craters on really big volcanoes like Mount St. Helens or Mount Pinatubo. These form when you get a giant magma chamber, lots of magma building up under the ground, under the volcano. Pressure builds up and up and up until eventually they erupt. This releases huge amounts of lava and gases, and all of a sudden this magma chamber empties. And then the mountain collapses into the magma chamber, forming a huge circular depression, sometimes several kilometres across, and forming something very like what we've got here.
So in our flour volcano, the magma chamber was actually represented by the balloon, and when we cut the knot off, it was just like an eruption.
Yeah, that's right. All of the air inside the balloon in the real-life magma and gases erupted up through the top of the balloon, throwing some stuff up into the air, and then the hole which was left, the flour collapsed into, forming a caldera.
But if we've got all of this liquid rock, the magma that was in the chamber underneath it, why doesn't it all just harden again into the same mountain shape?
Well, in a really big eruption, the stuff which erupts out, the magma and also lots of ash being thrown out, it basically gets thrown further away than the size of the volcano. In big eruptions like the Mount Pinatubo, ash was thrown thousands of kilometres, in fact, all the way around the Earth.
How big can these things get?
One of the biggest volcanoes we know of is, in fact, the whole of the Yellowstone National Park in America. This is several hundred kilometres across, and it's a big depression, which is in fact a caldera formed exactly like this, in an absolutely immense eruption which released thousands of cubic kilometres of magma and ash, and probably did very bad things to the climate when it went off.
So the entire of Yellowstone National Park is in fact one big caldera, one big crater like we've just made in our flour.
Yeah, that's right.
That's quite scary, really. But surely once this has happened, once there's an eruption big enough to cause this and everything settles back down into the now empty magma chamber, surely that's the end of a volcano's life. It can't have any more volcanic activity after that, surely.
Well, if you've still got magma rising from deep beneath the Earth, then there's still stuff to drive the volcano. Probably the first eruptions after the caldera forms will be quite small, where magma escapes as lava and just forms a kind of blob in the centre of this caldera.
So what you end up with inside the caldera is actually lots of little volcanoes where there used to be one huge one.
Yeah, you'll get lots of small eruptions for a while until possibly the small eruptions manage to block up the escape for the magma, and so the pressure can build up, and then maybe you'll get another big eruption.
So does this mean that the big crater in Yellowstone National Park, which when it erupted must have wiped out most of North America, I guess, does this mean this could explode again?
No reason why not, and there's definitely lots of people doing lots of research on that subject at this very moment.
Well, I do hope that they can keep studying it and warn us before anything drastic happens. But in the meantime, you can make your own volcano at home using only some flour and a balloon. That's all for Kitchen Science this week. Dave will be live in the studio with you next week for another live Kitchen Science.
Scary stuff, and it must be a huge eruption to create Yellowstone. Flour and balloons sound like a much safer way to go. And there are lots more Kitchen Science experiments, and a write-up of the experiment you just heard on our website, nakedscientist.com/kitchen science.
So thank you very much also to Ben and Dave for doing that terrific experiment, which has spawned lots of questions, actually. Marie, we've heard from Dave in Peterborough, and he says, can you just give us a quick update on the situation with Yellowstone? What's happening there?
Well, as Ben and Dave were just telling us, Yellowstone is a huge system, and between eruptions, which generally happen every 600,000 years or so, it's not a dead system. Instead, the magma chamber is inflating, and indeed we can see that now at Yellowstone, a very slow rate of deformation, but it's certainly inflating, preparing for its next eruption, which probably won't happen in our lifetime.
Thanks, Marie.
And Yildiz has emailed us. He asks, how do you find water underground? Richard, can you tackle that one?
Well, all rocks, all sedimentary rocks contain water. What we're really looking for is rocks that have porosity and permeability. So you can look at outcrops to find out which are the right suitable rock types, and you can drill holes and hopefully intersect those suitable rock types. So all sediments contain water, and it's actually when they're buried that you're actually squeezing the water out very slowly. So it's really a matter of looking for the suitable rock types. For example, chalk underneath London is a fantastic aquifer, has been historically anyway.
Thanks, Richard. Marie, got a question here from John in Colchester. He says, can underground nuclear bombs or explosions result in shockwaves that might trigger off a volcano?
Well, to my knowledge, this has never been observed, but in theory, yes, because certainly distant, very large earthquakes can set off volcanic eruptions, so presumably this is possible.
And Richard, one would think that they might have an impact on mud volcanoes.
Absolutely. That's proven that earthquakes can kick off mud volcanoes, and if you go down onto a beach and jump up and down on the shoreline long enough, you'll create your own sand volcanoes. It's exactly the same sort of process. You cause something called liquefaction when you turn the sediment into a liquid.
And so, have we actually any evidence linking earthquake activity or bomb tests, anything like that, to mud volcanoes, really, or is it just theory?
Well, I mean, now I've investigated the Lucy mud volcano. I heard of stories where mud volcanoes erupted at the same time as seismic surveys, etc. I don't know if it's proven yet, but it's certainly been suggested. And if there's already a mud volcano there, in other words, the pipeworks is there already, it could happen. It could increase in its activity level.
Thanks very much, Richard. We'll have to leave it there. That was Richard Davies from the University of Durham. Also, thank you very much to Marie Edmonds from Cambridge University. We've run out of time, I'm afraid. I have to now say thank you to our wonderful production team here. That's Diana O'Carroll, Petra Minch, Mira Thillingham, Ben Vassler and Dave Ansell. Next time, it's our science phone-in show where you send in the questions and we try and answer them for you. So please send your questions to chris@thenakedscientist.com and we'll do our best to include them in next week's programme. Thank you very much for listening. My name's Chris Smith. We'll see you next time and good night.
The Naked Scientists are sponsored by the Wellcome Trust, the EPSRC and UK Fast. For more information, look us up online at nakedscientists.com.